Hello, game theorists. So we showed how to depict simultaneous move games. We also saw what a Nash equilibrium was. Now we gotta know how to find Nash equilibria. There are three main tools. So the first tool is strict dominance. So we say that strategy X strictly dominates strategy Y if it always gives a higher payoff regardless of what everyone else does. So to find a Nash equilibrium, you can eliminate all strategies that are strictly dominated. And all the ones that are strictly dominated be the ones that survive, and one of those could be the Nash equilibrium. Now, to be clear, after you've eliminated the strategies that are dominated, the strategies that remain might or might not be a Nash equilibrium. If there's only one outcome left, that's the Nash equilibrium. But sometimes there are some strategies that survive the elimination process and they aren't necessarily equilibrium. So let me try to be clearer here. A Nash equilibrium is never strictly dominated. So if I get rid of strategies that are strictly dominated, I'm just simplifying my task. I know I'm not eliminating a Nash equilibrium, so by reducing things that are not equilibria, I can narrow my focus on which outcomes possibly could be an equilibrium. Let's see how it works with the prisoner's dilemma. So we had Ty and we had Rachel. And they could either confess or not confess. We will start by looking at Ty's strategy. So let's say Rachel's going to confess. What should Ty do? Well, in that case, Ty is our role player, so Ty's payoffs always come first. So Ty looks at these first numbers here. If Rachel's confessing and Ty also confesses, he's getting minus 12. If he plays not confess, he gets minus 20. That's worse. So if Rachel confesses, Ty is better off confessing. The other possibility is that Rachel could not confess. So Rachel's strategies here are in the columns, because Rachel's a column player. If she plays not, we're in this second column over here. Row players' payoffs always come first, so Ty cares about these numbers, the 0 and the -1. So if Rachel is not going to confess, Ty could get 0 by confessing. Alternatively, he could get -1 by not confessing. That means that Ty is better off by confessing. So as you can see, regardless of what Rachel does, either way, Ty should confess. If Rachel plays confess, Ty should confess. If Rachel plays not confess, Ty should still confess. So what you can do to eliminate the dominated strategy is you just draw a line through it. So that's indicating that Ty is never going to play not, because not is strictly dominated. You could go through the same exercise for Rachel, or you just keep following this process of elimination. So we established that Ty is going to confess. So Rachel's got to pick, should she confess as well, or should she not confess? So Rachel is the column player. Column players' payoffs always come second. That means Rachel's going to focus on these numbers over here. So she either gets -12 from confessing, or she gets -20 from not confessing. It's better to get -12. So that's going to eliminate not for Rachel. So after making that elimination, there's only one outcome left. That's confess, confess. So that is your Nash equilibrium, which we found by eliminating the strictly dominated strategies. Now, to be clear, I said last time that the Nash equilibrium is the strategies, not the payoffs, and I gave that some emphasis. So confess, confess are strategies. If you'd written Nash equilibrium -12, -12, that would be wrong. -12, -12 is the payoffs, not the strategies. So just always with the strategies, because that's unique, sometimes you get the same payoffs through a different set of strategies, so that's not always unique. That's why it's always strategies, never payoffs in the Nash equilibrium. So that's our first example with strict dominance. Now, I'll contrast that with a related concept that is called weak dominance. We say that strategy, let's say strategy S, weakly dominates strategy T if it gives a payoff that is at least as high as T no matter what the opponents do. So it's a little bit different from strict dominance. So with strict dominance, you have to actually have a higher payoff, not at least as high, but actually bigger, greater than. This is more like greater than or equal to. So while you can always eliminate strategies that are strictly dominated in your quest to find a Nash equilibrium, you can't do that for weak dominance. There actually are examples, and we'll see one shortly, where a weakly dominated strategy is part of a Nash equilibrium. So we had this example we talked about in the previous episode. So we had A, B, and C, and we had X and Y, and our two players were Joanne and Jerry. So in that earlier episode, we found that Bx was a Nash equilibrium. However, it turns out that A weakly dominates B. Let's verify. So, as always, the row player's payoffs always come first. Joanne is here on the rows picking row A, B, or C. So Joanne cares about these first numbers in the table. So if Jerry is picking X, we're going to be over here. Joanne can get 0 by playing A or 0 by playing B. Doesn't matter, they're the same. So A and B are equal if Jerry's picking X. If Jerry plays Y, though, A is better than B. So A is always at least as good, if not better, than B. So A weakly dominates B. So if you had eliminated strategies that are weakly dominated, you would eliminate B, but that would be eliminating a strategy as part of a Nash equilibrium. Now, there is a strategy here, though, that can safely be eliminated. Do you see it? If it's not immediately obvious to you, go ahead and pause the video and think about it, and when you're ready, press play. Alright, so assuming you've given that some thought, it turns out that strategy C can be eliminated because C is strictly dominated. It actually turns out that both A and B strictly dominate C. So you can see that quite easily because C always gives Joanne a negative payoff. Joanne's payoffs come first, whereas these ones over here give her a 0 or positive. So I can just cross out C safely. No problems there. So the moral of this story is that you can always eliminate strictly dominated strategies, but you can't eliminate weakly dominated strategies. A strictly dominant strategy always gives you a greater payoff. Weakly dominant means greater than or equal to payoff. Now, as you can see here, it also illustrates a point I made earlier. Once you eliminate a strictly dominated strategy, that can help you narrow down your search for Nash equilibria, but it might not on its own give you all the Nash equilibria. There's still some more work to do to find the Nash equilibrium. So in case you're wondering, is strict dominance still useful even though it doesn't always get you all the way to the answer? It is still useful. We'll see that especially in some of the later chapters. If you get a game that's really, really complex at the start, especially games that involved randomization, it can really help a lot to chop out one or two strategies that are just bad, that are strictly dominated. So it is still a useful tool, even if it doesn't always get you all the way to the Nash equilibrium.